We now want to talk about what we would call weak chemical bonds, and we're going to talk about two different types. The first ones are the hydrogen bonds. If we read through the definition here first, it's when we have a hydrogen atom covalently bonded to one electronegative atom that is also attracted to another electronegative atom. All right, so we're going to break it down and look at that definition in parts and pieces. If we look at the water molecule here up at the top to start with, for this water molecule, we've got an oxygen that has, I draw it here so we can see it in more detail. We've got an oxygen that has a bond to a hydrogen over here and another hydrogen up here at the top. And when we look closely at these bonds, these are actually polar covalent bonds. So that means that our electrons would be up here, which is going to make the oxygen a little bit negative and the hydrogen's a little bit positive, just like we discussed before. So that's the first part of the definition, okay, because if we stop right here, we have a hydrogen atom covalently bonded to one electronegative atom, which is the oxygen in this case. If you have that particular situation, it is going to be a polar covalent bond, and that will make the hydrogens a little bit positive. Now, if we look down here as well, we've got ammonia, and ammonia is NH3, and ammonia is very similar to a water molecule in that you have something that is very electronegative, nitrogen in this case, that is sharing electrons with hydrogens. And so you have in this one 3 polar covalent bonds, which makes the nitrogen a little bit negative and the hydrogens a little bit positive. Now, if these molecules happen to be close enough together, this hydrogen that's a little bit positive will be attracted to this nitrogen that's a little bit negative. So that's the second part. So if we have a hydrogen atom covalently bonded to one electronegative atom, it's going to be a little bit positive and it will be attracted to another electronegative atom. So we have that example right there. The dotted line is representing the hydrogen bond. It's basically an attraction of charges, similar to what we have with the ionic bond. So the opposite charges are attracted to each other, so they're somewhat sticking together. If we look at a bunch of water molecules, this is what gives water a lot of the properties that it has. The water molecules always have a negative end and a positive end, and so if they get close enough together, the hydrogen end can be attracted to another water molecule's oxygen end. And so you do see lots of hydrogen bonding between water molecules. This is what provides the surface tension that allows insects and leaves and things to actually float on the surface of water. So hydrogen bonds, we are talking about weak bonds, but generally you do have more than one. So you might have a whole bunch of them. If you think about the structure of DNA, DNA has millions of hydrogen bonds lined up along the middle of those two kind of strands that make up that double helix, which you've probably seen a picture of at some point. If we look at this in regards to larger molecules, here we have a bunch of hydrogen bonds represented by the little pink lines here. If we go through here and we identify some of our polar covalent bonds, this one right here would be polar, here would be polar. Actually, all of the bonds surrounding this nitrogen are going to be polar, which is going to give us little negative areas and little positive areas. So that's a positive right there on that hydrogen. If you look over here, this is going to be a polar covalent bond, and the oxygen is going to be a little bit negative and the carbon a little bit positive. Down here, a little positive on our hydrogen, a little negative on our nitrogen. These would also be polar. Okay, so if we just look, you do have, where you have all of the little pink dotted lines representing the hydrogen bonds, you do have a hydrogen covalently bonded to one electronegative atom, so it is a part of a polar covalent bond. It's a little bit positive and it's going to be attracted to an electronegative atom that happens to be a little bit negative. So those are our hydrogen bonds. We're going to see those quite a lot this semester. In regards to DNA structure, which we've already mentioned, RNA structure will also have them holding together a lot of the protein three-dimensional shapes as well that we'll discuss in quite a lot of detail in Chapter 5. The very last type of bond is going to be the van der Waals interactions. Now, van der Waals interactions are due to the fact that electrons move constantly. So what that means is that not only is the electron moving constantly, but the negative charge around an atom is also moving constantly. So if you took a snapshot of an atom, at one moment this end might be negatively charged and this end would be positively charged, and then the electron's going to keep moving. So the next moment it's going to be flipped, and the next moment it would be flipped, and so on back and forth. So it's continually changing, but there is kind of a rhythm to it. If you had another molecule that was kind of along the same rhythm, this one for one moment is going to have its positive charge across from this one's negative charge. And that little dotted line there is representing the van der Waals interaction. So it's an attraction of opposite charges. Now it's only going to last for a moment because very quickly the electrons are going to move again. However, if these molecules are in sync with each other, when they do move, you're going to still have the opposite charges across from each other. So they will still be attracted to each other. So these are called transient interactions, meaning that they don't last very long. They're very short-lived interactions, but they're enough to hold together some relatively weak things. So this is what allows a lot of insects and lizards to actually crawl up walls or crawl across a ceiling. So it is important for some biological reactions. We'll see them involved in DNA structure and protein structure as well in later chapters. Now, water is going to be extremely important to living organisms. First off, because living organisms are composed of a lot of water. So as we go into more detail talking about the structure of a cell, we'll discuss how the majority of a cell is water. And in addition to that, if you think about the environment that living organisms are living in, they're living in the presence of a lot of water as well. So just the Earth's surface, we say, is covered by about 75% water. So obviously water is going to be extremely important to living organisms, and we need to understand the properties of water. So if we start discussing water, if we say the molecular formula of water, we would say H2O. And you've probably used that H2O term at some point in your life. Now what that molecular formula is really telling us is what atoms or elements are present in water and how many atoms we actually have of each one. So when we look at H2O, we can see that water does have some hydrogen and it also has some oxygen. And then in addition to that, we can see that we have 2 hydrogen atoms and we also have 1 oxygen atom. Now we assume that the oxygen, we're going to have 1 of those because we don't see some other number there written beside the oxygen. If we tie in another molecule we looked at in chapter 2, methane was one we looked at quite a lot, and methane is CH4. When we see that CH4, we have 1 atom of carbon, and again we assume that it's 1 because we don't see some other number written there, and we actually have 4 hydrogen atoms. Now what the molecular formula fails to tell us is how those atoms are actually arranged and connected together. So if we need to know how they're connected together, so where the covalent bonds are actually at, then we need to look at a structural formula. So the structural formula of water is written right here. And that structural formula tells us that we've got an oxygen atom that has a single covalent bond to each one of the hydrogen atoms. We can see by looking at that formula that the 2 hydrogens are not actually connected together at all. We can see that those bonds that we have, they're single covalent bonds. So if we had double or triple covalent bonds, they would be shown in the structural formula. And in addition, when we see those covalent bonds, we can also look at them and we can now differentiate between polar covalent bonds and nonpolar covalent bonds. Now in this case, with water, these happen to be polar covalent bonds. They're polar covalent bonds because the oxygen is extremely electronegative and the hydrogens are very weak. So this means that the electrons would actually be held much closer to the oxygen end of the molecule. And keep in mind that those electrons have a negative charge. So this means that the oxygen end is going to be a little bit negative and the hydrogen ends are going to be a little bit positive. If we go to our methane example again, methane has a carbon in the middle, and that carbon is surrounded by 4 hydrogen bonds, each connected to the carbon with single non-polar covalent bonds. Now, because water has those polar covalent bonds in it, we do have the 2 different ends to the molecule. So we refer to water molecules as polar molecules. Polar because they've got opposite poles, or 2 ends that are behaving differently from each other. This is going to give water a lot of unique properties that you may not see in other molecules. If we just look at a population of water molecules, then you would see that they interact with each other based on opposite charges. So opposite charges attract. Well, if you happen to have one end of the water molecule that has a positive charge, that would be your hydrogen end, it would be attracted to an oxygen end of a neighboring water molecule. So you will see lots of hydrogen bonds between water molecules. And this gives water a lot of unique properties that we see in nature. For example, when you see a drop of water on a leaf surface or on the surface of something else, that water drop is not flat, so it is raised up. And it's raised up because those water molecules are connected to each other by hydrogen bonds, and that's holding that water droplet into kind of a ball or spherical shape. Now, your textbook spends quite a lot of time going through some of the properties of water due to its hydrogen bonding that you do see in nature. So take a look at that. They're not going to be covered in this presentation. And pay special attention to the discussion in the textbook about solid water, which would be ice, liquid water, and gas. And take a look at how the hydrogen bonding between the water molecules is going to be different depending on the actual state of the water. What we do want to spend a lot of time on in this chapter is talking about water's ability to serve as a good solvent. Water is a good solvent because of its polarity. That polarity goes back to the fact that we had a molecule that had a positive end to it, which would be the hydrogen ends, and it had negative ends to it, which would be the oxygen end. So if we define solvent so that you have an idea of what we're talking about here, a solvent is going to be the dissolving agent of a solution. Okay, so what that means is it is something that dissolves molecules. If we look at a common example, if we take salt and we throw it in a glass of water and we stir it up, we know just from our everyday experience that that salt is going to dissolve in the water. So in that case, the water would be the solvent because it's doing the dissolving, and then the salt is going to be the solute. So the solute will be the substance that is actually getting dissolved. If we do get all of that salt dissolved in that water, that's going to be what we then call a solution. So a solution will be a completely homogeneous mixture of 2 or more substances. So in other words, we've gotten our solute completely dissolved in the solvent. Now, there are a number of things that can dissolve in water, and that's why we call water a very versatile solvent. If we look at some examples of how water is able to dissolve other molecules, a good example is sodium chloride. So sodium chloride is our normal everyday salt. Okay, so that's table salt. And sodium chloride is what we call an ionic compound because it is composed of 2 ions interacting with each other. We have a sodium ion, which is what we would call a cation because it has a positive charge, and we have a chlorine ion, which we call an anion because it has a negative charge. And opposite charges attract each other. So those 2 stick together just because they have opposite charges. Now if we go back to our water molecule, if we draw it now like a little V, the pointed end would be your oxygen end. It's going to be a little bit negative, and the hydrogens would be on the 2 other ends. That water molecule has positive charges and it has negative charges, kind of pseudo charges, that can also interact with opposite charges. So if we throw some salt into a glass of water, there's lots of water molecules floating around. And what's important is that the oxygen ends, which are the negative ends, are going to see the sodium and they're going to start to surround it. Notice how I've turned all the V's so that the negative end, which is the oxygen end, is going to be surrounding the sodium. And they will eventually completely surround the sodium so that we have our sodium with little V's basically coating the surface of this. We call this little surface coating a hydration shell. So a hydration shell is just a little sphere of water molecules that's going to coat the surface. Now if we go back to our chlorine happens to have a negative charge, so that means that the other end of the water molecule will actually surround the chlorine. So we're surrounding the chlorine with the positive or hydrogen ends. So this will occur until we get the chlorine basically completely surrounded by its own hydration shell. So when we talk about water dissolving things, it is interacting with charges. Basically, opposite charges are attracting each other. So the water has one end to it that has a partial positive charge, and it has one end that has a partial negative charge. So if you have ions in solution, or that you're throwing into your water-based solution, the water is certainly going to be able to coat the surface of those. So it will surround that ion with whatever end happens to hold the opposite charge. So what we see in this illustration is that water is very good at dissolving ionic compounds. Ionic compounds basically have charges, and water has charges as well, and it can interact based on opposite charges being attracted to each other. So if we define that solution that we just drew, that would be what we call an aqueous solution. We call it an aqueous solution because it is a water-based solution, or in other words, it is a solution where the water was the solvent. It was actually doing the dissolving. In this picture, you're just seeing a better representation of the salt grain that's actually being dissolved in the water. Notice how those water molecules surround the two different ions, putting their oppositely charged end around the ion. So with the sodium, we see the oxygen ends of the water molecule surrounding it, and with the chlorine, we see the hydrogen ends of the water molecule surrounding it. So the water that we have in the solution will slowly pick apart each one of those ions that makes up that grain of salt until eventually every single one of those ions is going to be coated by a little hydration shell. If we can do that, then we will get a solution. So we will have a homogeneous mixture of molecules. So the different regions of the polar water molecule can interact with ionic compounds through electrical attractions. Opposite charges attract each other. Now, in addition to that, water can also dissolve things that do not have charges. So it can interact and dissolve non-ionic, which means non-charged molecules, so long as they are polar molecules. So if we think about sugar, you've probably dissolved some sugar in the kitchen before, so you're familiar with the fact that sugar does dissolve in water. Well, if we look at an example of a sugar, this would be a very simple sugar. In this case, if I draw it right here, when we draw this simple sugar, this very small sugar molecule, if we can see the structural formula, which is what I've drawn here, we can see that a lot of those covalent bonds are going to be polar covalent bonds. If they are polar covalent bonds, that's going to create a lot of little positive areas and little negative areas in the molecule. So if I just label some of those, and again, this is strictly due to the fact that we've got some polar covalent bonds here. Sorry, that should be a negative there on the bottom. If we label those little areas of charge, that gives the water molecule something to interact with. So if you have a region that has a negative charge, like we see down here, then we would have the hydrogen ends surrounding that. If we have an area like we do up here that has a positive charge, then the oxygen end would be surrounding that area of the molecule. So the key here is that if we have a molecule that has a charge to it, or if we have ions, they obviously have a charge, then water will dissolve it. Additionally, if we have molecules that have lots of polar covalent bonds to give us lots of little positive areas and negative areas, the water will also be able to surround that. So the water needs to be able to see some kind of a charge there so that it can orient itself so that opposite charges are then attracted to each other. If you look at this purple molecule in the picture, notice that the water molecules are turned in all different directions because you will have different areas of charge scattered over that surface. So if we introduce some terminology, these things that we've been looking at in the last couple slides are what we would call hydrophilic substances. Hydrophilic substances are defined as substances that have an affinity for water. The term hydrophilic basically is broken down to mean water loving. So these are things that want to mix with water. So you could say that they mix with water. We could also say that they are soluble in water. But we just looked at examples of things that would be hydrophilic. So if we're talking about things that are hydrophilic, they're going to have either real or kind of partial or perceived charges in them. So if they have that, then the water molecules are going to be able to coat the surface and make that hydration shell that we just looked at. If we look at this example here, the molecule is shaded in blue. This molecule has lots of polar covalent bonds. If we have polar covalent bonds, then we've got little areas that are negative and little areas that are positive. And if I go through here and quickly label them on this diagram, hopefully you can see that anywhere we have a negative charge, you've got the hydrogen end of the water next to that. Anywhere that we have a positive charge, we've got the oxygen end of the water molecule close to that. So to identify a hydrophilic substance, it really goes back to chapter 2 and being able to differentiate polar versus non-polar covalent bonds. If we happen to have a lot of polar covalent bonds, then we will have a hydrophilic substance. Or if we have an ionic compound, so something that's made up of ions of different charge being attracted to each other, that will also be soluble in water. Now, for things that are not soluble in water, these would be what we call hydrophobic substances. So hydrophobic substances, the very word means essentially water-fearing. Okay, so these are water-fearing, which means that they don't mix with water. So this is essentially just the opposite of what we looked at, or they are not soluble in water. So little or no affinity for water would be another way to say it. Basically, if you think about oil, you can add oil to water, but it does not want to mix with that water. That is a good example of something that is a hydrophobic substance. If we're talking about hydrophobic substances, what makes them hydrophobic is that they have lots of non-polar covalent bonds. If we have lots of non-polar covalent bonds, then basically the water molecules would rather hydrogen bond and interact with each other than this molecule which has no charges or partial charges within it. So keep in mind that the water molecules will stick together, and this means that the non-polar molecules will stick together. So the oil molecules will stick together and make a little droplet or a ball of oil inside your glass of water. So it really all boils down to the fact that like mix. Keep in mind that water is a polar molecule and water dissolves polar things. So polar stuff likes to mix with polar water. If we're talking about non-polar substances, they would mix very well with non-polar things. A good example of a non-polar solvent would be acetone. Okay, so there are things that will dissolve those non-polar substances, but water is not one of them. If we move on now and we talk about acids and bases, we are going to be dealing with aqueous solutions when we're talking about our reactions inside of a living cell. And it's important to understand that water molecules, when they are in solution, they do not always hold together in the H2O form. So what that means is that they tend to fall apart, and when they do fall apart, they fall apart into basically a hydrogen ion, which we see right here, which is H+. And we also get one ion that we call a hydroxide ion, which is an OH-. Now, one water molecule will fall apart into one of each of these. Notice that one is positively charged and one's negatively charged, and opposite charges attract. So that means that this is also going to be a reversible reaction. So water molecules are going to constantly be falling apart into these two ions, and then they will also be reforming back into the classic H2O. If you have a bunch of water in a glass, some of the water will be together, some of the water will be apart. Now keep in mind as well that if you do have a water molecule that is polar, and water molecules are always polar, we have one end that's going to be a little bit negative, and then we have the hydrogen ends that are going to be a little bit positive due to that polar covalent bond. And if we have extra hydrogens floating around, they could get stuck on here to that negative oxygen end. So we can end up with what we call hydronium ions, which are H3O. Now, we're not going to talk a whole lot about hydronium ions in here. But what is going to be very important to us is going to be the concentration of the hydrogen ions that we have in solution, because those are going to ultimately determine what we call the pH of a solution. Now, in pure water, which we don't normally have, but if you do have pure water, one water molecule is falling apart into one hydrogen and one hydroxide ion. So in that case, we would expect to have equal amounts of the two. So if we were to draw this as kind of a balance here, you've probably all seen the teeter-totter balances before, we've got an equal amount of hydrogen ions and hydroxide ions. That would be pure water, or what we often call a neutral solution. Most of the time we don't have pure water. Now, what we call acids and bases are substances that disrupt this balance between the two. So in other words, if we add an acid or a base to a solution, then we now have the scale tipped in one direction or the other. So if we talk about the acids and the bases, an acid is going to be any substance that increases the hydrogen ion concentration such that now we're going to have extra of the hydrogen ions. So if you had, if we draw this, get us a blank screen here. Suppose that we have pure water. Pure water, we have equal concentrations of the hydrogens and the hydroxides. So I'm just going to draw equal concentrations of both of them on this slide. So at this point, we've got that nice balanced scale. Now, if we take a classic example of an acid, which is hydrochloric acid or HCl. HCl, if you dump this into solution, it tends to fall apart into a hydrogen ion and then also a chlorine ion. So if I go and I dump some of that into my little container here, I'm going to dump it in, it's going to immediately fall apart into hydrogen and chlorine. If you now count up how many hydrogens you have compared to the hydroxides, you will see that our scale has now been tipped in this direction, such that we have extra hydrogens compared to the hydroxides that we have. And the more hydrochloric acid we dump in here, the more unbalanced we will become. So an acid is going to basically increase the hydrogen ion concentration such that we end up with this situation over here, where we are unbalanced. We've got too many hydrogens compared to the hydroxides that we have in solution. Now we do also have this little chlorine here in solution. That does not affect what we're talking about with the relationship between the hydrogens and the hydroxide ions. Okay, so here we're really looking at the relationship between the two, whether we've got an equal concentration of them or whether we have more hydrogen or more hydroxide, as we'll see in the next example. A base, in comparison, is going to be any substance that reduces the hydrogen ion concentration. So a base is essentially going to tip the scale in the opposite direction, and we have two ways that that one can actually operate. If you look here, we have one example with with ammonia right here. Ammonia has a very similar structure to a water molecule. We've got basically a nitrogen that's attached to 3 hydrogens. And we talked previously about the fact that oxygen and nitrogen were extremely electronegative. So in this case, you've got 3 single polar covalent bonds, which means all of those electrons are over here near the nitrogen. That makes the nitrogen end a little bit negative and the hydrogen's a little bit positive. What that means is that if you were to throw this into a glass of water where there's a lot of hydrogen ions floating around, those hydrogens are attracted to that negative oxygen end. So they do attach, and we end up with what we call NH4, which does happen to have a positive charge there. Now, if that happens, we are essentially removing some hydrogens from solution. Now, when we say removing hydrogens, the hydrogens are truly there still in the solution, but they're going to now be bound hydrogens. So if we look at this, if we draw our equal concentrations of both, if we throw some NH3 in here, so ammonia in here, suppose this hydrogen is going to make its way over here, it's going to attach, so we're going to change this to be NH4. This one's now attached over here. When we talk about that little balance, we're really talking about the free floating, or in other words, the unbound hydrogens and hydroxides. So once this extra hydrogen was bound up, it does not factor into this equation or this balance anymore. So notice in this case, after we add the ammonia, we end up with extra hydroxides compared to the hydrogens that we have in solution. So one way that a base can operate is by actually taking the hydrogen ion concentration down, so they can decrease the hydrogen ion concentration. If they do that, then that is going to tilt the scale to be heavy on the hydroxide side. Another way that they can operate is, as we see this second base example, sodium hydroxide operates by increasing the hydroxide ion concentration. If the hydroxide ion concentration goes up, or if we add hydroxides to solution, then it will also tilt the scale in that direction. So sodium hydroxide tends to fall apart into a sodium ion and a hydroxide ion. This will increase the amount of hydroxides that we have in solution compared to the hydrogen ions. So what we want to keep in mind is that neutral solutions or pure water have equal concentrations of both the hydrogens and the hydroxides. If we add an acid is going to make us have extra hydrogens compared to the hydroxides. And if we're talking about a base is going to tip it in the other direction so that we've got extra of the hydroxides.